Now let's look at 2024 F equals MA problem 17. This problem gives us a very complicated system that consists of pulleys, ropes, springs. Okay, and it says the following thing. So let's look at this mass M, right? So the problem says that so for a given M, the system equilibrium is in some position, and once we increase the mass from M to 2M, then the system's equilibrium positions will be adjusted, right? And it asks us to compute the displacement of the end of the rope. So for example, when it is hand with M, suppose the height from the ground is 10 meters, and once the mass is double, so the height from the ground is reduced to be 7, so the answer is 3, okay? And this is how I want to solve this problem. I don't want to first compute the positions with M and 2M and compute the difference. So I want to use the massless one as the benchmark. What I mean is, so first I try to study or begin with the system that the mass here is 0. And then I define an equilibrium positions for everything. Because if the mass is 0, so there is no gravitational force anywhere, right? So all springs are at their relaxed length, right? So that's a simplest case. So I'll use that one as the benchmark. And then I will analyze the scenario that, so once we have the mass, and then what will be the displacement from the ground? And then, so for the mass is equal to M, I compute one number. For it is equal, mass is equal to twice of M, I compute another height. Then I take the difference. So that is the answer. Okay. All right. So now let's begin with looking at the benchmark system that the mass here is equal to 0. So the entire system is massless. So in equilibrium, we know that the system is with the 3 springs that are with the relaxed length. Okay. So in equilibrium on the top, so everything is massless. Okay. So this is the thing we need to define, okay, for the benchmark scenario. So let me define the height from the ground to the center of the lower pulley to be h0, okay? And let me assume that in equilibrium, on the right-hand side, so here it is hand with the mass, right? So in benchmark, it is equal to 0. So let me assume that its initial position is that it is at the same height as the center of the lower pulley, okay? So I define the benchmark position in such a way, because later we need to use h0, okay? All right. And now let's look at this new system that the mass here is gained some mass, say from 0 to some number called M. And let's see how the system changes. So once we have the mass, let's first look at the bottom spring with spring constant 3K. We know that because it is connected to the mass. So now its length is extended. So it can apply a force to balance the system. And the force that is applied by this spring, or the force that this spring applies to its 2 ends, should be equal to M times G. So this allows us to compute its extension, denoted as x3, which means that, so by having M, its length is extended with the vertical displacement x3, okay? So we can compute x3 is equal to mg divided by 3k. All right. Next, let's look at the upper half of the system. For the upper half, this is what we know. So let's look at the whole system here. So Now I want you to look at the two pulleys and the mass M and the bottom spring 3K as a system. So let's do the force analysis on this system. So the system experiences the following external forces. There are two applied by the top two springs with spring constants K and 2K, right? And at the bottom, mass M experiences the gravitational force mg. And also, the bottom of the 3K spring is connected to the ground. Because to make the 3K spring to be in equilibrium, the ground applies the force mg onto it. So basically, at the bottom for the whole system, there are two mg's. One is the force applied by the ground. The other is the gravitational force. And on the top, they are balanced. So 2mg is balanced by the joint force applied by two upper springs. So for two upper springs, because they need to be extended, right? So let me call the extension of the left one as x1, the right one as x2. So we have the equilibrium that k times x1 plus twice of k times x2 is equal to twice of mg. And also, if you look at the upper half, if you choose the center of the upper pulley as the reference point, so the net torque should be 0. So that requires the force on the left and right springs should be balanced. So we have the equation kx1 is equal to twice kx2. So by solving these two equations, we get x1 is equal to mg over k, and x2 is equal to mg over twice of k. Okay. So after calculating the displacement of the upper two springs, so we know their joint effect is they will jointly lower the position of the upper pulley. So let me say the displacement of the center of the upper pulley as x. Then we have x is equal to the average of x1 plus x2. It is equal to 3mg divided by 4k. Okay. All right. So next, let's look at the rod that connects the two centers of pulleys. So the rod has a fixed length. Therefore, once the upper pulley is lowered by x, then it entails that the lower pulley is also lowered by x. Okay. So basically, now its height. Recall the original height is h naught. So the new height is h naught minus x. Okay. All right. So our job now is to compute the distance between the mass and the ground. And now we are ready to quantify this distance. So let me take out this part from the diagram and do the particular analysis. Okay. So for this distance, let me call it h. What h is equal to? All right. So suppose I know h, then I can compute the length of the left part that comes from the spring and some part of the rope, and the length on the right part of the pulley. Okay, so let me compute the total length. So on the left, it should be equal to h naught minus x. On the right, it is equal to h naught minus x minus small h that we are going to calculate. So what's the total length? Recall that in the original system, both halves had height h naught. So the total length, suppose we ignore the half perimeter of the pulley because the rope actually lies on the upper half of the pulley. So let's just ignore that. Okay. So this sum up the length on the left part and the right part. So on the right part is 0, right? And then on the left, it has height h naught. So it is equal to its original length. But this is not enough. because the 3K spring has an extension with X3, so it has been extended, right? So the total length of the spring plus the rope that cross the lower pulley should be equal to H naught plus X3. Now we are ready to compute H. H is equal to H naught minus twice of X minus X3. Let's plug the numbers to this expression. So recall that X is equal to this one, 3 mg over 4K. X3 is equal to mg over 3K. So height is equal to this one, okay? So basically it tells us the following thing. In this entire system, right? So those originally its mass is hand here, so the height is h0, right? And once it has a mass m, so it goes down with this displacement. So this problem asks us to compare two the cases. One is the mass is m, another is the mass is 2m. So we'll need to compute their differences. So their difference actually is simply just equal to this number. Okay, so this is the answer. Then E is correct.